Now we move on to what are called tier 2 models, and we'll start off with a discussion of the simplest model in this tier, namely the well-mixed room model. And this figure shows conceptually what the model scenario looks like. So we have a worker in a room, and we know the volume of the room, and there is a particular process that is generating contaminant into the room air at a rate of g milligrams per minute. Air is coming into the room at a rate of q cubic meters per minute, and air therefore is leaving the room at the same rate, q cubic meters per minute. Because we cannot have the inflow and outflow of air being different, because then you could have a situation where your room is becoming pressurized or depressurized, which we are not considering. In the most general case, we could also assume that the incoming airflow already is contaminated with the same contaminant, and if there is a certain concentration in the incoming airflow denoted as Cn, we can also assume that some of the contaminant could be removed from the room air by processes such as adsorption or absorption onto the room walls, or the settling of airborne particles onto the floor and onto the walls. And the output of this model is the concentration of this contaminant in the room air, denoted by C room. We are also going to assume that the emission rate is constant throughout the time period of interest. So the emission rate is denoted by G milligrams per minute. It's important to point out at this point that there are very few sources that satisfy this description, meaning that the emission rate is perfectly constant. But it is a reasonable assumption in many situations. So using a constant emission rate in a model fails to capture the intensity of peak or short-term exposures. If these peak exposures are important in terms of toxicology, then a constant emission rate should not be assumed. But if it's not important, if these peak exposures are not important, then making this assumption is perfectly reasonable. So if toxicological regulatory interest focuses on the 8-hour time-weighted average exposure level, then assuming a constant emission rate is reasonable. And why is that? If we consider an 8-hour shift as the period of interest, and if the same total contaminant mass is released into the room air either as one pulse, a series of smaller pulses, or uniformly over the shift average concentration will be the same. The other assumption that this model makes is that the room is considered a perfectly mixed box. So perfect mixing means that the contaminant is dispersed instantaneously throughout the room to create a uniform concentration. The concentration is the same at 1 centimeter versus 10 meters from the source. Again, we can intuitively understand that perfect mixing is physically unrealistic. Assuming perfect mixing can lead to seriously underestimating exposure intensity for an individual located close to a point source of contaminant emission, because the exposure intensity is greater closer to the emission source in general. So, although perfect mixing is physically unrealistic, the well-mixed room construct provides a reasonable exposure estimate in 3 situations. Number 1, for individuals working in the room at some distance from a point source. So, for example, greater than 2 meters away. For all individuals working in the room about 2 minutes after emission from a point source ceases, and for all individuals working in the room if the emissions are from a large surface area, for example, painted walls. So in these kinds of situations, the well-mixed room assumption is reasonable. So if you have not a point source that I showed in that conceptual diagram a few slides before, but if the emissions are from walls that are painted and the emissions are from the walls, that is a distributed source, and we can assume that no matter where the worker is in the room, they are exposed to the same concentration. And so the well-mixed room assumption makes sense. So the well-mixed room model and the other models that we'll be discussing in this course are what are called as mass balance models. And in each of these models, we essentially keep track of where the mass of the contaminant is. It is similar to what we did in the example of the Henry's law constant, where we kept track of the mass of benzene that was initially completely in the water and then distributes itself between the water and air. So we are going to build the well-mixed room model by considering the processes that lead to what are called contaminant gains, meaning the contaminant increases in the air, and then contaminant loss terms, meaning what are the processes that reduce the contaminant in the air, and then what are the processes that cause the concentration to change. And so we essentially create an accounting of the mass or a mass balance equation. So what are the contaminant gain terms? So there are two possible sources of the contaminant in our simple scenario. So we have number one, the in-room source. So there is a source that is generating contaminant into the room air at a rate of g milligrams per minute. We also know that the contaminant can enter the room through the supply air at a concentration of Cn, again in units of milligrams per cubic meter. And so the rate at which this mass moves into the room is the product Cn in units of milligrams per cubic meter times Q in units of cubic meters per minute. So the product has units of milligrams per minute. What are the contaminant loss terms? So we can consider four possible pathways by which contaminant is removed from the room air. The first one is that some of the contaminant is washed out of the room by the exhaust airflow. That has a value of Q cubic meters per minute. The rate at which the contaminant mass is exhausted from the room air is the product of the room air concentration, C room in units of milligrams per cubic meter, and the airflow rate, Q in units of cubic meters per minute. So that the product of these two terms is again milligrams per minute. We also have the possibility that some of the contaminant molecules could adsorb onto room surfaces. Number three, some of the molecules could be removed from the room air by chemical reaction, decomposition, or transformation so that that molecule no longer exists. It has converted into a different molecule. And then finally, if we are looking at airborne particles, the particles could also be removed from the room air by processes such as gravitational settling. So the removal rates via the processes of adsorption, molecular reaction, particle settling are denoted by parameters such as K2 for adsorption, K3 for the molecular reactions, and K4 for particle settling, respectively, and have units of per minute. And so these are fraction of the contaminant mass removed per unit time. These rates are usually difficult to estimate. And so, for the sake of simplicity, we are going to gather all of these non-ventilation removal rates into a single removal rate constant called case of L, L standing for loss. And the rate at which the contaminant mass is removed from room air is denoted by this equation below. So the way to understand this equation is to look at the second and third terms first. So you have the room air concentration in milligrams per cubic meter times the volume of the room in units of cubic meter. So the product of these two terms has got units of milligrams. So that is the milligrams of contaminant in the room. And so what fraction of that contaminant is removed per minute? So that is denoted by the term case of L. So if you multiply the case of L by the mass of the contaminant, that product now of the three terms also has units of milligrams per minute. So now we can summarize the mass gain and the mass loss terms. So the gain terms You will recall we have the in-room source. It has units of milligrams per minute, G. We have the contaminant coming in through the room supply air. So that is the product of Cn times Q. That also has units of milligrams per minute. What are the loss terms? So we have the air in the room being exhausted by the product of C room times Q, again in units of milligrams per minute. And then the loss due to other pathways such as adsorption, chemical reaction, or particle settling. Product of K of L times C room times V. And this also has units of milligrams per minute.